Hi, I'm Cassie, and I'm going to walk you through question 21 of the AAMC's official physics question pack. So this question gets at two really important concepts for the MCAT. The first is the idea of the reflection of light, and the second is the idea of the refraction, or the bending of light. So let's start with a quick review of the reflection of light. Let's say I have a mirror. We all know that mirrors are reflective surfaces. So the first thing you're always going to do in these problems about reflection or refraction is you're going to draw the normal. And the normal is just a line. I usually draw it as a dotted line, but you can draw it as a solid line that's perpendicular to wherever your surface is. Okay, so this is going to be my normal line. So then we have a ray of light, which I'm just going to draw in blue here. Hits our mirror, and then what happens? It's going to hit the mirror at a certain angle from the normal. So we're going to call this theta I for the angle of incidence. Incident just means like the light that hits a surface. And then it's going to, I'm going to draw a little arrow here to show that that ray of light is hitting our mirror. And then it's going to reflect back. And that angle here, this angle of reflection, theta r, is going to be exactly equal to our angle of incidence. So here we have theta I equals theta r. And that is what we call our law of reflection. This doesn't just apply for actual mirrors, it also applies to surfaces that act like mirrors, to any reflective surface. So for example, water, when it's calm, it can act like a reflective mirror, and light can bounce right back off of it. So that's the law of reflection. But let's talk about refraction, because it applies in this question too. So let's say instead of a mirror, we have very calm water. Again, I'm not going to draw it perfectly flat because, of course, water is never perfectly flat. But for the purpose of this question, you can consider the water to be flat. And then, of course, I'm always going to draw my normal line, which is perpendicular to the surface that our light ray is hitting. And so above the water, we have what? We have the sky, right? We have air. And then, of course, below our surface, this is all water here. So we have two different mediums, right? Air and water. And our light ray, it's going to start out in the first medium, the air. So there's our incident ray, right? And then when it enters into the water, that water has a different, what we call optical density than the air, which means that although the light ray was traveling at a certain speed in the air, it's going to change speed when it enters the water. Specifically, water is more optically dense. So the light ray is going to interact more with the particles in the water, which is going to slow it down. And the effect of that light ray getting slowed down is that it's going to bend towards the normal. So if this was our theta I, our incident angle, this is going to be, we'll call it our theta alpha, which is going to represent our refracted or our bended light ray, right? So we know that in this case, since light travels faster in air and slower than water, we know that our incident angle is going to be greater than our refracted angle, our theta alpha. And there's a mnemonic that can help you remember when light travels from a less dense medium to a more dense medium, like from air to water, it's going to bend towards the normal. Versus when light travels from something like water to air, something more dense to less dense, it's going to bend away from the normal. So that mnemonic I use is FST, fast. In other words, when light travels from fast to slow, then it's going to bend towards the normal. And how do we represent how optically dense a medium is, which tells us how fast light travels through it? Well, we use something called the index of refraction. So the index of refraction is just a number that's going to tell us how much the medium bends or refracts light, or in other words, how optically dense the medium is. For example, the index of refraction of air, which we're going to call N, is always just going to be 1. So you need to remember that for the MCAT. You should just know that off the top of your head. The index of refraction of air is 1, versus the index of refraction of water, which is more optically dense, so light is going to travel slower through it, is going to be about 1.3. So the bigger than your N, the bigger your index of refraction, the more optically dense the medium is. So the more the light is going to interact with that medium, and the slower light is going to travel. And therefore, the more that light is going to bend towards the normal if you go from a less dense medium to a more dense medium. So quick review of our important parts here. So we said our index of refraction, which we represent as N usually, is how much a medium is going to bend or refract that light. The more optically dense the medium is, the more it's going to bend that light and slow it down. So again, the higher our index of refraction, the lower the speed of that light is going to travel. And then we know that if we go from a lower index of refraction medium, like air, to a higher index of refraction medium, like water, then we're going to bend towards the normal. And you can use the mnemonic FST. When you go from a fast medium to a slow medium, you bend T towards the normal. Or the opposite also applies. When you go from a medium with a higher index of refraction to a medium with a lower index of refraction, then you're going to bend away from your normal. So what's happening in our question here? Well, we know that we have a ray of light and it's starting out in the air, the question tells us. So immediately when you see that, the fact that it's mentioning air, you should think, oh, index of refraction is n equals 1. And so we have a beam of light that is traveling through our air like this, so that would be our incident ray. And then it's entering into another medium. And the medium that it enters into, we're told, has a index of refraction of 1.5. So a higher index of refraction. So what should I be thinking in my head? I should be thinking of my mnemonic, FST. We're going from a medium in which light travels faster, air in this case, to a medium where light travels slower. They don't tell us what the medium is, but they tell us it has, an index of refraction of 1.5. So we're going from a faster medium to a slower medium. Then that means we're going to what? We're going to T. We're going to bend towards the normal. Okay, so if this is our incident angle, which we're told is theta, we know that we're going to bend towards the normal. So therefore, this angle, once we've bended, which they're calling alpha, we know what? We know that alpha must be less than our theta because we bent towards the normal.
Okay, so now what happens? Well, our light ray is going to hit our bottom surface here, and then it's going to reflect off that bottom surface because we're not changing mediums here. We're just staying within the same medium. So it's going to reflect back here. When that reflection happens, we could draw in another normal line here, right? Which is just perpendicular to our bottom surface here. And then this angle, our incident angle, we could call, let's say, beta. I'm just going to call it a B for beta. And then, of course, since our law of reflection says that our incident angle equals our reflected angle, this angle right here is also going to be beta. Okay, so then when this reflected ray goes back up towards the original surface, the transition between the medium with a 1.5 index of refraction and the air. So if we draw another normal here, right, perpendicular to our surfaces, then we know that this angle here must be alpha, right? It's got to be the same as this angle over here. So what do you notice, right? Well, this angle was alpha when it went from our air into our new medium. And then this angle by default we called beta, so then it reflects back at beta. Now it's back to that same alpha angle again. We know that when it transitions from the medium with an index of higher index of refraction to a medium with lower index of refraction, it's going to bend away from the normal. So essentially we're doing the opposite of our original transition. So we're going to bend back away from the normal here, and the end result is that this angle, which we're going to call theta prime, is going to be equal to exactly our original theta. So I'm going to write that here. Our theta is going to be equal to our theta prime. So just to review one more time what happened, right? Well, we had a ray of light. It was traveling through air. It hit a new medium at a certain angle theta. Then that new medium had a higher index of refraction. So the ray of light bent towards the normal here at an angle alpha. That ray of light then hit the bottom of that medium with an index of refraction of 1.5 and was reflected back upwards. And so we can call this angle at which, the incident angle that it hit the bottom of the surface beta. And so it was reflected back at angle beta 2. If it was reflected back at the same angle beta, then this angle here must be angle alpha. So we're going to do the same transition again that we originally did from air to the new medium, except in reverse. Here we're going from, the new medium with the higher index of refraction back to air. And so our angle theta prime here is going to be exactly the same as our original angle theta.
And therefore the answer choice for you that probably reflects that is answer choice B. So I hope this helps. If it helps, give it a like and follow my channel for more content like this.